Hello, I would like to welcome you to my talk entitled Sub-2-Cycle Carrier Envelope Phase Stabilized 100 Watt 1.1 millijoule laser system. My name is Steffen Hädrich. I'm with Active Fiber Systems, a fiber laser company in Jena, Germany. And the work that I'm going to present has been done in collaboration of different institutions in Jena, Germany, as well as the ELI Alps research facility in Szeged in Hungary. And first of all, I would really like to thank the organizers to give us the chance to present here today in a bit more extensive manner than usual. Okay, in the beginning, I would like to motivate a little bit what ultra-short laser pulses are used for. They can be used for pump probe experiments, XUV generation. They have found applications in biomedical sectors. When using XUV generation, they can, of course, also be used for XUV imaging or for photoelectron spectroscopic experiments. And in general, these applications require a high peak power, a high pulse energy to enable those applications. And on the other hand, to improve measurement times and signal to noise ratio, a high repetition rate, and high average power laser system. So Active Fiber System is a company that can deliver those demanding requests in terms of pulse parameters. We have been founded in 2009, and our mission is to rapidly transfer research into a reliable, commercially available system. Our main market lies in research, that is fundamental research, materials processing, or life science. And today we are a technological leader for high power, ultra fast fiber laser systems. We recently moved into our new building, which you can see here in the background, with more than 1,500 square meter of lab space and more than 1,000 of square meter of office space. And as you can see, over the recent years, we have been rapidly growing. So our systems have been installed all around the world. So as you can see here, some exemplary system in the labs of the customer, which are located in the US, across Europe, in Asia. Our products itself have a large range of possible output parameters. So we have compact 1 micron laser systems in 100 watt class, but we can also deliver high average power 1 micron systems with kilowatt of average power. These systems can be combined with Few.cycle add-on or CEP stability, XUV beamlines, but we can also offer 2 micron lasers and several add-ons such as OPA, SHG to extend your wavelength range and the range of applications that you can address, or bursts and more compact picosecond lasers for nonlinear microscopy. So as I have mentioned in the title already, this talk is about the combination of our high power ultra-fast ytterbium laser system at 1 micron and the generation of Few.cycle pulses combined with CEP-stable operation. So of course, the main driver of our R&D efforts here is the ELI Alps research facility in Szeged, Hungary. It's devoted to offer users world-class parameters of isolated attosecond pulse generation, and the primary resources, that is the laser systems itself. 2 of those 6 main laser systems will be at high repetition rate. So as I said, to drive attosecond beamlines here, these systems are the HR1, the high repetition rate laser number 1 at the development phase number 1, which those parameters are shown here. So the HR1 is operated at 100 kilohertz, 1 millijoule, 100 watt, 6.2 femtosecond, and with CEP stability. And as you will see, I will outline how we have achieved those parameters here. And HR2 is currently in development. So the main difference here is that the pulse energy is about a factor of 5 higher, with otherwise more or less identical parameters. And this is going to be installed in the next year then. Okay, so let me briefly outline how this system looks like. I will already start with the HR2 laser system. HR1 is very similar in its concept. So the front end is a CEO stabilized oscillator, which is sent into a preamplifier stage. This preamplifier stage already includes the pulse stretching, pulse picking, and spectral phase shaping. And then the main part is the 16-channel main amplifier system that can be used to obtain very high average power output. And finally, the pulses are compressed in a CPA pulse compressor to a pulse duration of about 300 femtosecond. So as I said in the previous slide, for the HR lasers, we want to have a Few-cycle output, and to achieve this, we employ spectral broadening, and I will outline in the following a little bit on hollow core compression, but also on multipass-cell pulse compression, which has been recently demonstrated even at Few-cycle output. And of course, this also requires a temporal compression to finally provide the CEP-stable Few-cycle output here. So for the CEP measurement and finally the stabilization, we split part of the output beam, send it into a stereo above threshold ionization pulse meter, which generates us a signal that can be fed back to an element in the preamplifier to stabilize the CEP here. So alternatively, we can also offer to have the direct CPA output available, but also, since this is a two-stage compression approach, as you will see in the following, we can also offer a 35 femtosecond output here at the same time as the Few-cycle output. The two main challenges regarding the R&D efforts that we have done here are, of course, to achieve CEP stability. So this has been a multi-year effort from our side, and of course, to achieve these Few-cycle pulses at unprecedented average power levels in the final output. So this is actually a photograph of the HR2 laser as it is right now. So this is the lab, and actually I can really encourage you to visit our website. So we have a virtual lab tour where you can actually also access this laboratory of the HR2 laser. So I really recommend to take a tour and have a look on your own. So here we have a bit more of a detailed outline of the 16-channel main amplifier fiber, or main amplifier fibers. As you can see, there are two levels of operation, so 8 fibers on each of the levels and 4 on each side. And these 16 channels can be arranged very compactly due to the use of fiber lasers here. The system output can be as high as 1 kilowatt with this 16 fiber channel system. At 100 kilohertz repetition rate, this is more than 10 millijoule of pulse energy. And as I said, the pulse duration is a bit less than 300 femtosecond. But what is remarkable here to note is that the average power stability over 9 hours is as good as 0.3% RMS deviation. At the same time, we can offer excellent beam quality with a measured M square of 1.2 at these full output parameters. And the beam pointing is extremely stable with only 6 and 12 microradians in X and Y direction, respectively, also measured over this 9 hour of operation. So, as I said, the pulse duration of 300 femtosecond is still too long for the required Few-cycle output, and therefore we were investigating different post-compression approaches. The first approach we followed is to use an extremely long stretched hollow core fiber. And this stretched hollow core fiber has the advantage that it has no bending, so that is, we have the lowest possible propagation loss in this setup, and that gives us the confidence that these fibers can be used for high average power lasers as well. So in the particular experiment we did, the fiber lengths that were tested are 6 and 8 meters. So I will present mostly 6 meter results in the following, with 400 micron of inner diameter in the hollow core fiber, and we fill this fiber with argon gas, where we had sort of pressure gradient with 800 millibar in the beginning and a high pressure of 1900 millibar at the end of the fiber. So we did the first set of experiments. In this case, we used half of the available amplifier channels, 580 watt of average power, 5.8 millijoule of pulse energy, 300 femtosecond pulses. We coupled those pulses into this stretched hollow core fiber. And then, as you can see here, we ramped up the input power, and the output power, which is shown with the blue dots, linearly follows the input power. which also translates into the transmission, which is shown in this orange curve here. And on this axis, that this transmission remains nearly constant or almost constant up to this 580 watt of input power. We achieve more than 300 watt of output power, and at the same time with an excellent beam quality, as shown here by this mode profile that has been recorded at the maximum output power level. Of course, we also went on to compress the pulses. So the first thing to note is that we achieved a significant spectral broadening, as shown here in the lower graph. And then this D-scan measurement that we did gave us a reconstructed pulse duration of a bit less than 10 femtosecond pulses measured by this D-scan method. So that means we have almost 320 watt of average output power, which is still the highest average power Few-cycle lasers that has been demonstrated. The repetition rate was already at 100 kilohertz, so that means a bit more than 3 millijoule of pulse energy represented, and the pulses were as short as 3 cycles in duration. However, when we went on to scale this, in particular to shorter pulses, it became obvious that for increasing the bandwidth in the hollow core fibers, we would have to use even much longer fibers, which at some point, of course, becomes an issue with the footprint, and also the losses increase. So therefore, the recent advances in Few-cycle multipass cells were very encouraging to us. So this is actually a result from the University of Jena, where they recently showed that by using a 500 watt tritium CPA system, they can compress this in a first multipass cell to about 30 femtoseconds with almost 500 watt left still, so very efficient in this first cell. But what's even more important, they realized a second cell where they showed almost 400 watt of output power out of the cell. So still very efficient, a bit less because of using metal mirrors. And they compressed a bit less than 1 watt of this output power to a 7 femtosecond pulse duration. So that means these advances clearly show that the transmission efficiency of multipass cells is much, much higher. The experiments from the University of Jena prove that it's a power scalable approach, and they actually show in this publication that calculations show that they much higher average powers can be expected, and that they can provide the required bandwidth to achieve this Few-cycle pulse duration at the output. And that led us to the conclusion that this is a very promising concept for the HR type of laser systems that we are talking about here. So we went on to build our own realization of such multipass cell compression. So we start with 8-channel fiber CPA system. So this is the HR1 laser in this case, with only 180 watt. So the system is actually designed for 300 watt. So it can be run at a much more relaxed parameter range, 1.8 millijoule, 300 femtosecond pulses that we sent into a first multipass cell. This is actually this cell shown here, which is based on dielectric mirrors. And that, of course, leads us to an extremely high efficiency. So more than 95% of throughput efficiency with 170 watt, 1.7 millijoule, 35 femtosecond pulses that can be obtained out of this first multipass cell. So the second cell is actually shown on this picture here, based on metal mirrors or enhanced silver mirrors on monocrystalline silicon, as demonstrated by the university group in Jena. And as you can see already on the picture, we achieve significant spectral broadening. So we can already see visible light here, and the efficiency is still so high that we achieve 107 watt, about 1.1 millijoule at the output, with a pulse duration of only 5.8 femtosecond. So actually this is the highest compressed average power Few-cycle multipass cell that has been presented so far. And here I would like to show a few more of the measurement results that we obtained with this system. So as I said, about 1.1 millijoule, more than 100 watt output. This is the measured pulse. Pulse duration has been measured once again with a D-scan device. It's faintly shown here on the background of the computer. We also measured an excellent beam quality. The measured M² is less than 1.1. And in particular, on-site at ELI, we measured the stray ratio to be 0.98. So it's an excellent beam quality, extremely short pulse. In addition, we also could show that the long-term stability is remarkable. We measured only about 0.1% of power fluctuations over this 8-hour span that we have shown here. So these short pulses, good beam quality comes with an excellent long-term stability. And as I already mentioned, this has been recently installed on the HR1 laser. So this is these two multipass cells that we have seen before operating at the ELI Alps research facility. So the second important R&D effort that we had to tackle was the stabilization of the CEP. And we figured out that there's two major parameters of the system that we need to take care of to achieve good CEP stability. And the first one is the timing of the pulse picker. So the first thing is that we implement a CEP preserving pulse picking, but then still we saw that we have a strong dependence of the white CEP noise on our picker timing. That is the position of the TTL window to pick out the pulses from the pulse train was very important. And we found that the acceptance range is actually very narrow, with less than 1 nanosecond of precision to time this window with respect to the pulse train. So to give you a bit of an idea what the influence of this parameter is, here we have a measurement of the CEP. And in this case, what I will always show is integrated CEP noise. So these are these curves here that integrate to a certain value. And then on the right axis, we have the CEP noise power spectral density, frequency resolved, both of these plots. And we here focus only on the high frequency part. So this axis starts at 1 kilohertz and goes to 50 kilohertz. So that means we look at all the noise that we obtain above 1 kilohertz in our system. So initially we start out with a phase noise of more than 800 milliradian. And then if we optimize this picking ratio, you can see that the base level of this high frequency noise goes down significantly. And this also shows in the integrated phase noise here on the red curve. And with this, we can improve the level from 870 milliradians to 640 milliradians by only tuning the delay of the TTL with respect to the laser pulses by 0.3 nanoseconds. The second important aspect is the amplified spontaneous emission, which is a natural source of random phase noise. And we took a great deal of improving the ASE contrast to obtain a good CEP stability. So first of all, ASE is determined by the saturation, that is mostly by the seed power. So that means we need to have enough seed power for each of the amplifiers involved. And this is actually where we can really pinpoint the critical areas in this regard, that are the amplifiers that have to compensate high loss elements. And most prominently, this is the pulse picking itself. So we have about 30 dB of average power reduction when we reduce from our 80 megahertz oscillator to the 100 kilohertz pulse chain that we want to have in the end for the operation of the system. So the obvious thing is, besides general ASE optimization along the amplifier chain, that we started to distribute the loss between several elements with intermediate amplification. And most prominently, we actually splitted this pulse picking step into 2 steps. So, and by doing so, we find that, as shown here, is a spectra of the front end, where we have used 1 AOM, it's shown in the gray curve, and 2 AOMs with a red curve. And as you can see, the in-band ASE is reduced by 2 orders of magnitude. And this also shows quite prominently in the CEP noise. So once again, we start out at about 800 milliradians in this case, and we can reduce the high frequency or white noise level by a great deal to only about 310 milliradians for noise frequencies above 1 or 2 kilohertz. So these two things were very important for us to achieve a good CEP stability at the final output. As I said, key aspects are pulse picking and ASE contrast. And then we went on to measure the final output with a stereo ATI pulse meter. Actually, in this case, a commercial device distributed by Single Cycle Instruments, a small company also here in Jena, Germany. And this ATI pulse meter allows to measure a single shot and each and every shot of our 100 kilohertz pulse train. So that means we have the full frequency information of our CEP behavior, which is important to judge the system performance. So as already indicated in this figure here, the ATI pulse meter provides us with a so-called phase potato plot, so an asymmetry plot of electron energies. And in the case of a random CEP, this is shown here, the so-called potato, so a full circle. So each of the dots, or the angle of the dots, represents the CEP. And if we implement our CEP stability, that is oscillator stabilization, and our active feedback, we can clearly concentrate those points onto a small part of the circle, which indicates that we have CEP stability in the system. So we can further analyze this by once again doing or retrieving this frequency resolved plot of CEP power spectral density shown here in the red curve. And then we can do the same integration of the CEP. And as you can see here, for the frequencies from 10 Hertz to 50 kilohertz, we have a CEP stability of 400 milliradians RMS, which is already really good. Okay, so in summary, I've presented that we have a long-term stable 10 millijoule, 1 kilohertz, 300 femtosecond fiber CPA system, which is used to drive the ELI HR2 development, has also been used to for finalization of HR1. And we have investigated different spectral broadening approaches. So first of all, we were using a hollow core fiber, which can provide us high average power Few.cycle output, but was lacking a little bit in bandwidth. And this could be improved by using the latest advances in Few.cycle multipass-cells. And with this two-stage multipass-cell approach, we were able to provide more than 100 watt, 1.1 millijoule at 100 kilohertz with a pulse duration of 5.8 femtoseconds. So that's less than 2-cycle, so a sub-2-cycle output. And with excellent long-term stability measured to be 0.1% over a time span of about 8 hours. So this is actually the highest compressed average power Few.cycle multipass-cell that has been demonstrated so far, and also the first CEP-stable 1 millijoule 100 watt class laser system that has been presented. We are actually right now in the process of scaling this approach to also implement this into the HR2 laser system, that is to use this 10 millijoule CPA system and a multipass-cell compression approach to realize the HR2 parameters, which are 500 watt, 5 millijoule, less than 6 femtosecond pulses, and also combined with CEP stability. And as I said, this is ongoing work in our labs. So we were also able to pinpoint some of the key aspects to achieve CEP stability at the final system output. We could show that the pulse picking and the ASE contrast are two crucial aspects that need to be considered to finally realize the CEP stable output. And currently we can operate the system at 400 milliradians of CEP stability, again, measured and integrated over the full frequency range. So that's including all the noise that is present. And we are currently improving our front end further and also our feedback mechanisms. And we are confident that we are able to achieve sub 300 milliradian CEP stability very soon. And with that, I would like to really thank you very much for your attention.